Cool, my slides sort of match the background. That's awesome. I'm going to be here talking about Electron, WASM, and Rust, but mostly about WASM, as is highlighted on this particular slide. This talk is kind of a bit about everything and some of the things that I've experienced putting WASM in production. But this kind of title is a little bit ambiguous, so I'm kind of narrowing it down to a little bit differently. So you're a JavaScript developer and you're thinking of putting Rust to have WASM running in your main application, and I want to tell you all about it and how you can do it as well. Cool. So I work on a tool called Compass. It's a MongoDB GUI, or kind of like an IDE that lets you explore your data. And this talk is about one of the things that I've written that was previously written in JavaScript that now runs in Rust. And I'm going to be telling you all about how that works out. But primarily, this talk is also about how I've improved performance by writing parts of the application to now work in Rust. And we're going to talk a little bit about these numbers afterwards. This is like a little teaser. So hello, I'm Irina. I write JavaScript, and I write Node, and now I write Rust at MongoDB. I make zines also. I didn't bring any with me because I forgot to print them at the office before I left, and it was a bit hectic. But I make zines, and you can find them on GitHub as well. I've made one on the event loop. I've done one on Rust traits and how those work. I've done some on how the async ecosystem works in Rust. But I grew up in Vancouver, which is why I might not sound German. I get introduced as I'm from Germany, and that's where I live now. I live in Berlin, in Germany. I also have 2 cats. This one's Chashu. I'm also into, our cats are named after food, which is, I guess, the theme of the conference, naming your cat after food. This one's Chashu. That's a pork chop in Japanese. That comes with your ramen. That's the other one. This one's Nori, like seaweed. She's very good. This is the 2 of them together, parallelizing hunting for birds on the balcony. They're very good programming cats. But anyway, a cute little diversion about cats. But we're back to JavaScript and Rust and how that all kind of ends up working together. So I've got a little bit of an agenda that we're going to work through together today. First of all, why would you want to choose to work in WASM, and kind of the things that tie you to working to WASM and kind of the decisions you go from there. How to get to know Rust as a JavaScript developer and some of the things that I've experienced as a JavaScript developer getting into Rust. How do we end up working with WASM? How to debug WASM in your JavaScript environment? And where to go from all of this. After we've received all of this information, where do we go? Cool. So why do we want to go choosing WASM? There's a bunch of different things that people have written about working with WASM and why it's so incredibly fast and why you would want to go choose about it. But aside from all the articles, what is WASM even? How do we go about it? What is it again? There's a bunch of different definitions about it. One of them is from me, which it just says faster than JavaScript. But there's some more intelligible ones out there. But ideally, what it basically comes down to is that it's a low-level assembly-like language that comes into like this little tiny small binary format that you can then use as a compilation target from whatever language you're writing your code in, which essentially boils down to the fact that it's a compilation target, so we need something to compile that down from, which essentially can be done from a whole bunch of different other languages, like Go or C++ or Rust, which is what I've used to compile down to WASM. And essentially what happens is that you have your application, which in my case is Compass, that talks to WASM, and WASM talks to Rust. And it could go the other way around. Rust talks to WASM, WASM talks to Compass, and things like that. So WASM is our compilation target that I use Rust for. But what it allows for us to do is to be able to have native code running in the browser. And what that really means, native code running in the browser, is that you have fast code running in the browser. And what it looks like is a little bit like this. It's a little bit gibberish. which I call as a work of art of WASM Dev Tools. If you inspect it in the network tab, that's what it ends up looking at. But what do people use it for? There's a bunch of different use cases, and you can do whatever you want, really, like build games, do performance-driven applications. Lots of people do crypto, which is kind of the things that I haven't done before, but there's a bunch of stuff that's basically, it needs to be performance heavy. You can do it in JavaScript, but you could also do it and compile down to WASM and have it really fast. What we did is we've rewrote a parser that was parsing a bunch of documents in our application and made it really fast. So what it backs is something called that's in the schema tab, and this is kind of like the documents we're going to be parsing through, and when we want to analyze, this is the output that we get, and it accumulates a bunch of information about the set of documents that you work with, and then gives you details about this information. So for example, if we have a particular field, it could be a string or a double or an int. And we can see that information, and that's all powered by the parser. The schema tab also lets you accumulate and gather information and query from it, but that's more on the UI part of things. The parser is what is the backend and what we've written in Rust. And why did we write it in Rust? Well, the thing is now the schema tab only parses about 1,000 documents at a time, which lots of people have more than 1,000 documents in their database. So we kind of want to give them a more detailed information overview and maybe do more with that data afterwards. But what turns out is that if we work on even 10,000 documents, it's actually a really slow part of the process that ends up gluing we end up waiting on our UI to be able to parse stuff. And eventually, we don't want to have to do that. And there's a bunch of different ways of how else you can improve your performance. And some of them involve using web workers, maybe TypeScript, and you can also perform some V8 dark arts to be able to make sure your JavaScript is ultra fast. But we didn't do any of that. In fact, we just rewrote the thing in Rust, and now we're using WASM to be able to do all of that. And what that gives us is a pretty huge performance improvement. For 1,000 documents in a pretty complex database, it's not as apparent, but if you look at it, 10,000 documents, it's a lot more apparent as to how the performance improves. And that's a lot faster. Cool. So before we get into how did we rewrite the whole thing, let's talk about how this thing works. And it's a brief overview, so we're kind of on the same page. We have two things that power the JavaScript version of things. One is a collection sample that is a sampling that we're going to leave as is in JavaScript, and the other one's a MongoDB schema, all available on NPM and open source. And that one is the one that does the parsing and is currently in JavaScript that is also now in Rust. And they kind of communicate between one another. The collection sample queries a database and then returns a bunch of stuff to the document, to our Electron application, and MongoDB schema does the parsing. It's just a little stream that connects samples and then pipes, but the part that we're going to replace and we've replaced is this little pipe. Cool. But the data structure we're kind of dealing with is just kind of like this JSON object that then gets put into the front end. And all it does is that it gives us this accumulation of information about various things like the total number of count of this particular field type that is in people's documents given this 1,000 document collection, or the kinds of fields that we have and what they end up doing and things like that. Yeah. So we got into kind of what we're rebuilding, and let's kind of rebuild it and see how rebuilding of the thing works. So the first part is Rust. How does Rust play into the whole ecosystem? Well, let's take a look. We have the Electron application, Compass, that will still talk to the collection sampling, and we'll get some of the documents from the collection sampling from the database, and then get that all back into Compass. And then Compass will do the talking to Rust through WASM, essentially like that. And how the Rust portion of things happens, we'll take a look now. So kind of the Rust TLDR as to how I've gotten to learn Rust in the last 9 months and how that went along. It's basically a story of the number of times I did not do well. So I'm just going to tell you about all my embarrassing not doing well stories and how I've learned from those mistakes. It's a story of a lot of errors, like so many errors that sometimes it was a little bit difficult. And it's also a story of about a bunch of existential Googling, as I like to call it. Rust take immutable self, return regular self is one of the things I have Googled before. But the two things kind of like as a JavaScript developer coming to learn Rust, that kind of I've struggled with personally is the whole situation about types. And the whole situation about the ownership system or like the memory management system and how that plays out. And these kinds of things don't exist in JavaScript. We don't particularly have types. We have a garbage collector that does all the things for us, and you kind of get to miss it when you start writing Rust because you have to do a little bit of that work by yourself. And let's kind of dig into these and see how this worked out. So things are hard, but there's things that come and help you out along the way, and a bunch of these is Cargo, and which is the package manager for Rust. There's Rust-C, which is the compiler, Clippy, and Rust format that help you kind of make sure that your code is standardized and you're not making mistakes and you don't have those runtime mistakes that you would get normally when you have JavaScript running through. But Rust talks to Compass, and we're kind of on that side of things. So how does Rust talk to Compass? We want to be able to receive a bunch of documents, and we want to be able to put all of that information together and return a single document or a single JavaScript object that we can then work with in the UI parts of things. And to be able to do that, what I decided was the easiest way of being able to do that is just working with strings. Because it seems like it's the nicest way to be able to understand stuff, and seems like it's one type. I have one type, and I don't have to worry about any other types. So I started off with this, is that I have a write portion of my API that takes a JSON, which is a type of a borrowed string, and then what I return is a result type, one of arguments of which is also a string. So that seems all nice and dandy, and that worked really well, and I got a whole bunch of really good art from it when I was like debugging stuff, so it was good. But what ends up happening is that because we're dealing with people's data and people's documents, and this is a MongoDB database, we kind of have to care about the BSON types of things. So there's stuff like bin data or decimal 128, or being able to distinguish a double from a regular number and things like that. So regular strings didn't actually work in the very end. And what ended up happening is that I'd have to use a different crate that somebody else wrote. It's the BSON crate, so it's crates are like packages in JavaScript land. So the BSON one was actually a lifesaver. And so what then I was able to do is I would still accept a string, but then I would convert all these documents into BSON and be able to parse that information properly, more or less, to do what I wanted to do. One of the things as a JavaScript developer that we take for granted is that there is like this one number type that you get to deal with, and it's just, number. When you get to Rust land, and I was mentioning types before, there's a whole lot of different numbers that you can work with. So when you get to like being able to, be very good about your compiler and your memory management, you got to pick the right types for the right type of job and for the right amount of memory you want to use. So picking a number was actually like a very difficult decision. In fact, I made a flowchart to be able to figure out what exactly and how exactly I wanted to be able to use my numbers. And after all of this, I went through and I was like, okay, so I have all these numbers and I want to be clever about my memory management. I ended up having 2 fields that I needed to replace. And I just picked 2 of them. After all of that, just picked the U size to be able to use as much as I possibly can and not have to worry too much about whether or not I'm running out of memory by putting specific numbers in a particular type. Okay, so how do errors work? Errors are an interesting thing to be able to work with, because again, there's lots of different types. With Rust, a really good way of being able to handle an error is putting all of that into something called the box type. And it's a really good type, but all of this as a beginner is really confusing to be able to understand. And I just wanted like a regular, real, easy way to be able to deal with that data. So I used a crate called failure to be able to replace all of this with just failure error. And all of my errors ended up just being able to be propagated the same way I would handle the error normally, but without having to specify which particular type I wanted it to be, making sure the types match and the compiler is not angry, and all of that was good. So the second problem that I said JavaScript developers like myself have struggled with, aka I've struggled with this, is data ownership in Rust. And kind of the three things that are advertised with data ownership in Rust is that there's three different things you follow when you deal with data ownership. One thing is that each variable is stored in each value is stored in one variable, and that one storage is called the owner. And each value can only have one owner, so you can't have multiple things that can't have multiple objects belonging to two different things. It's only one owner. And when the value is dropped, it gets out of memory. So all of that is kind of managed by the compiler, so you don't have to do a lot of like allocate, deallocate as you would with C-style languages. You just kind of let the compiler handle it for you, but you still run into a whole bunch of different errors with all of that. And it's not fun, but eventually you kind of get a hang of it. So for example, this is my cat. Let path assigns a variable called Nodi, my cat, and that variable is the owner. We can then give that variable, we can borrow it to another variable called field, but that variable is borrowed, so that means path still has the ownership. You can also do other things to be able to have owners, like the Nodi to string is also now the owner, and that exists only in that particular function and does not exist anywhere else. Or if you want to use path in two different ways, you can also do toOwned, which duplicates that value and now gives it to field new. Or you can also clone, which a lot of people say don't do, but it's also fun and fine sometimes when you want to get the job done. So you can also clone it and then borrow it somewhere else. But the main thing is that you compile things and they don't work, and you compile things and you don't work, and then you get angry with a borrow checker, but the main rule here is that it's always right, or you don't fight it, because it'll always be right. And then you eventually just have to end up writing better code, and you kind of learn from your mistakes, and you develop into a better programmer, which I have, I think, by learning a bit of Rust. But you can also do a little bit of convincing with the compiler. I had this very good advice, which says, I like to think of the borrow checker as a cat, and that if you give it a box, it's usually happy. And a box is a type in Rust, which you can put a bunch of things in, and then it allocates the amount of memory that you might need, and a little bit of extra. And it's nice, you kind of don't worry about it, but not a lot of people, when you start off, know about box. So I tried putting cat in a box, and it worked. It also works if you just put it in the box type, which is the correct code. But this one's way better, if you could agree. Yeah, and so another thing is to be able to kind of convince the borrow checker is to be able to clone a bunch of values, which allocates some stuff, but in certain cases also gets the job done. Cool. So the Rust portion of things is done. It's under MongoDB Rust, MongoDB schema parser on GitHub, and it's all available and open source. But the next part of things is, how do we get WASM to work in this environment, and how do we debug WASM? So we've mentioned this before. Rust will talk to WASM, Compass will talk to WASM, and kind of the communication happens with the Rust code through WASM. So let's take a look. We've mentioned that this is a compilation target, and that's what we're going to be compiling Rust to. But how do we actually do the compiling of things? And the best way, the easiest way, is to be able to use the WASM bindgen crate. And that crate makes it incredibly easy for you to be able to compile. All you do is annotate your code. And it kind of generates two things for you. One is the JavaScript file, and one is the WASM file. And then you're able to just use WASM in your JavaScript through the bindings.js, which is really nice. But the way you do it is really easy. You just annotate it with WASM bindgen, and then all the magic happens there. And you can do other things with it as well, because some of the names are going to be very Rustified. You might want to use more conventional JavaScript things, and you might want to have a proper constructor that you could use as a constructor in JavaScript. And that is followed through with just giving it a constructor and a JS name. And you can do write_JSON is not very JavaScripty way of naming things either, so you can case it properly, and also you just do write uppercase JSON. And there's 3 different things that you can work with, 3 different types that you can work with. 1 is JS error, 2 is JS value, and 1 is a string. So it was a good thing I wrote everything with strings to begin with, because I did not have to do anything. I just kind of have to return the result as a string. I'm returning a string. WASM returns a string. Everything is happy. Let's build. Let's see if it actually works. And it didn't. It was really good. I was really close. It seemed so easy. And there was a bunch of errors that came through. And as I said, this is a story of a lot of errors. And so what ended up happening is that I have this result that was not very happy with my error type selection, which really meant I couldn't use failure error anymore. And I was really sad about that because I really didn't want to deal with all the error types that could possibly be handled. I had too many types to deal with at this point. So how do I handle this? Well, what I did is I had 2 different, I wrapped up all my WASM stuff around my Rust stuff. And then I just stringified the error and returned the error if I had the string, which is really nice. And it worked and did not really hinder my performance. It was just a little bit clunky. But it works. I like it. So you just kind of stringify all the errors. You match on the error, you stringify it, and return it. But the thing is, it's getting worked on. So a few other people have mentioned the fact that you just want to have the Rust errors to be able to work with your JavaScript. And it's nice that you're not the only one who's facing those kinds of issues. Cool. So we kind of started off this whole thing with a string, and we want to be able to deal with a string. But what happens is that a lot of the BSON data that comes through is BSON, and we want to be able to tell different types of BSON apart. And what the node driver can actually return to us is this raw BSON, so none of the data integrity gets lost. But how do we use it? Well, the nice thing about the raw BSON part is that it's basically just an array. So technically, an array in Rust is a vector. So I can sort of make all of this work. But I just said that we can only do these kind of 3 different types. And how do we go from there? Well, there's another crate that helps us distinguish other types that JavaScript supports. And it creates basically a bunch of raw bindings that you can have as JS APIs. And so there's a bunch of different ones, just like the object, the function, uint, array, date, iterators, things like that, available in JavaScript, also available in Rust through this crate. And so my vector that I wanted to use becomes available through uint array, which is really nice. I'm just using it as it is. I'm doing some vector magic to make it work. And then I decode the document and don't lose the data integrity. So a decimal 128 will return as a decimal 128 and not just like a squished up number and just a number. And I want to be able to know when a decimal 128 is a decimal 128, which is really nice. All right, so errors. Because we're using like kind of this JSSys crate already, what I'm able to do is actually be able to be very, very specific about my error types. So I can return a type error. I can also return eval errors, range errors, syntax errors, which is basically the errors you expect to be in JavaScript rather than just a regular string, which is really cool also. So how do we debug this whole situation? Well, debugging is hard. But it could be made really easy, and I'm going to show you how. So a bunch of the errors come in as through this. You get like this unreachable function, and then you get pointers to your WASM functions, which when you get this runtime error are not particularly useful because you click through the stack trace, and it does not get you what you want. And then you compile again, you test, you compile again. And then if you want, you can throw this type of error. And then what it gives you is that you have an error in your API endpoint, which is toObject. But really what it is not very helpful information because that particular API hides about 20 other different Rust functions. So how am I able to debug all of this? Especially when an error is just like recursive use of an object detected, which would lead to unsafe aliasing in Rust, which is like does not make a lot of sense. And so I kind of, at some point, I was like looking for this error and what it actually means, and which part of my API it was meant to be. And that, again, that API hides a bunch of stuff that's, difficult to parse through. And what is this to-object thing? And it kind of was interesting to go through kind of this WASM bindgen crate, and I had a borrow fail for some reason, and again, was not particularly interested in this borrow fail or this WASM cell, which I was not using. And so what kind of helped me is two things. One is I found out that I had unimplemented calls, which is basically just a panic, which turns into a runtime error, which was what my error was causing. But two, I kind of wrote this logger that prettifies the log files that you're able to use. But what I was able to do is in WASM, I was able to get Rust numbers to the lines. But I got Rust numbers working in JavaScript, which is interesting. And there was so many Rust numbers. I was console logging so much that it was really good to be able to just see where exactly the error was coming from. And the other thing that helped me out was this crate called console error punning hook, which basically hooks up to your Rust code and is able to tell you that sometimes you're using a thing, you're trying to index into a thing that is empty, and obviously you should not be doing that, and obviously that's a runtime error, and how did you ever think of doing this? Which is also really nice. So it's not as hard as a recursive use of an object, et cetera, et cetera. Right. Sometimes you get errors with other crates that you're using. So for example, there's things with Lipsy, and then you can write down kind of the stuff that you can compile only for WASM, or you can compile not for WASM. So for example, this one is in the bsong crate itself that was doing a bunch of indexing into getting process ID, which is system-specific. System-specific stuff does not really work in WASM. So I'm able to do things like, I want this particular implementation to work in WASM, and this particular implementation to not work in WASM. And that compiles really well. And the advice here is that be careful of the packages that you use that might underneath use Lipsy, because all of that stuff will not compile down. OK, so we're kind of back into this thing of we've got the WASM and the JavaScript, and how do we actually use it in our JavaScript application. And this part is really nice and easy, because while JavaScript appears, and we're able to just get it all to work with WASMPack. And what WASMPack does is that it compiles all of this application for you, and you're just able to npm install the thing and just use it as it is. So you can npm install the thing and use it as it is. And all that does is require you to be able to load it async. An async workflow is a little bit interesting, but all you have to do is just do an import of the file. And then when we get to import the file, we get a little bit of a whoops. Just Webpack. Again, a story of a lot of errors, quite a few of them, and they're all solved incredibly easily with just installing the right version of the Webpack and getting your Babel plugin with syntax dynamic import, which imports your JavaScript to be able to use it properly within the application. So what that looks like is an import, and then I have to promisify the schema parser load, and then use that parser as I intended. So I had a constructor that I just initialized the module, and then I'm able to just write the raw data as the API intends it, which is in my JavaScript application, which is nice. Cool. So the last part is, where do we go from here? Kind of a little bit of a retro, also, this little part. It was not the easiest thing to be able to learn Rust as we go. And to be able to do this on the job, and to be able to make sure that you kind of accomplish what it is that you said you would accomplish. But it was super fun to be able to do this. Rust has been able to help me, even in my JavaScript code writing skills, to be able to write more clean and programmatic code. But Rust specifically lets you write clean and programmatic code that is explicitly a lot faster, without having to resort to writing anything fancy. a friend wrote an article, Speed Without Wizardry. It's actually a very good read otherwise about WASM stuff. But basically what I think of WASM when I think of Rust is that you're able to do all of this good code without having to do any V8 dark arts. And being able to kind of take advantage of the Rust compiler and taking advantage of the ownerships and the type systems that it provides gives you a very predictable code with a lot fewer runtime errors. Even though I was showing you a bunch of code that had runtime errors, those runtime errors are a lot fewer than if just writing JavaScript. And what about WebAssembly? I'm a huge fan of WebAssembly, and lots of people come in and ask, is WASM our new future? And I want to say, yes, it's a new future. And WASM is really good to be able to write these performant applications. Would I rewrite my whole Compass app in WASM? I probably wouldn't. WASM is here to help your performance-intensive bits of code. But I would specifically rewrite only performance-intensive bits of code, like this parser, which was a huge performance-intensive bits of code. And I think of it as kind of like this sprinkler on a cake that you put on your application, and it's there to kind of help you out and write clean code. Cool. Thanks so much. Thanks for listening. Hope you enjoyed.